Let's do some more Newton's laws of motion problems for practice. We have a 5 kilogram block. It's being pulled by 15 newtons. What's the acceleration? Now you should pause the video and try each problem. You should write F equals ma to start these problems. Easy enough, right? Now what if I told you that we were doing this on a lab table and the experiment showed that the acceleration was 1.5 meters per second squared? We do an experiment, we find out that we have an acceleration of 2.5 meters per second squared. The velocity is to the right. You have to find the force of friction. Now pause the video before you continue. If the velocity is to the right, the friction's to the left. And it's kinetic. Start with F equals ma. Forces forward minus forces backwards. Mass times acceleration. We have a force of friction of 2.5 newtons. Hey, now we can find the mu k. Isn't that a blast from the past? Well, we know mu k equals the force of friction kinetic over the normal force. We have to go to the diagram to see the normal force. The weight of the block is 49 newtons, mg, and the lab table holds up the weight, and that's the Fn, and that's 49 newtons. So we have 2.5 newtons of friction over 49 newtons for the normal force, 0.051 for the mu k. It's a pretty smooth surface. That acceleration went from 3 meters per second squared only down to 2.5 when we included friction. Now imagine we have two carts and they're frictionless. We're going to pull this one with 25 newtons and they're attached by a string. Can you figure out the acceleration of this system? Start with F equals ma. We'll consider both carts to be the system. The force outside is 25 newtons. The mass of the system is 17 kilograms. We'll solve for A. And we get 1.47 meters per second squared. Both carts have that same acceleration. How do we find the tension in that rope? The tension pulls this cart forward, pulls this cart back. So we have a positive force and a negative force. They're going to cancel out when acting on the whole system. Remember, these are called internal forces if I consider both carts to be the system. So how do I find the tension in the string? I have to isolate one of the masses. We're going to break up the system, so now the tension becomes an outside or external force to this system. I can now apply F equals ma just to this cart. There's only one force making it go forward. The mass of that cart is 12 kilograms, and it accelerates at 1.47 meters per second squared, as we determined earlier. And I get a tension of 17.65 newtons. What would happen if I isolated this object? 25 newtons is acting on this cart in the forward direction. The tension is acting backwards. So it's forward minus backwards. The mass of that system times the acceleration. Hey, that's just what we got before. The tension in the rope is the same. Find the acceleration of this system of frictionless carts. If we view all three carts as the system, then there's only one force, external. The mass of the system is 20 kilograms, and the acceleration is 2 meters per second squared. And now I want to find the tension in the string. But there's two strings. Do you think those tensions are going to be the same? Let's isolate the last cart. The only thing accelerating it forward would be T2. T2 equals the mass times the acceleration of that cart. That tension is 14 newtons. Let's isolate the first cart. Strings can only pull. That tension has got to go backwards. The force forward minus the force backwards equals 5 kilograms for that system times 2 meters per second squared. Hey, these tensions are not the same. Let's take a look at the middle cart and we'll see why. What would happen if T1 was equal to T2 and they were both acting on this cart? They would add up to 0. The cart wouldn't be able to accelerate. Let's check that out. T1 is 30 newtons, T2 is 14 newtons. I'll have forward forces minus backwards forces. Hey, let's solve for A. And that's the acceleration of this whole system. It worked. That's why these tensions can't be equal. Now we have a 4-kilogram cart right next to a 16-kilogram cart, and I'm going to be pushing on this cart with 10 newtons. What's the acceleration of the system? I hope you got 0.5 meters per second squared. And now instead of asking for a tension in a rope, there's something else going on. This mass pushes on this mass through the normal force. Now just imagine if this pushes on this cart will push back on the first cart. These two forces are internal to this system. In order to find either one of these, we need to isolate one of these masses. Let's look at this cart. We have this normal force accelerating the 16 kilograms. So we have the normal force is equal to 16 kilograms times our acceleration of 0.5 meters per second squared. We have a normal force of 8 newtons. Let's go isolate this object. This cart has two forces acting on it, the 10 newtons pushing it forward and the normal force pushing it back. Using F equals ma, we have the force forward minus the force backwards equals the mass of the cart, which is 4 kilograms, times 0.5 meters per second squared for the acceleration. Hey, we get 8 newtons, it's the same as this. This is an example of an action and a reaction pair. You've probably heard about this. It's Newton's third law of motion. For every action, there's an equal and opposite reaction. In order to have Newton's third law of motion, you need two objects. One object pushes on this one. This object pushes back on the first. Here's a third law of motion classic. Two ice skaters. One pushes on this guy pushes back automatically. If the guy on the left pushes the one on the right with 20 newtons, the one on the right will push back 20 newtons also. So maybe these forces are the same, but will the accelerations be the same? F equals ma. I'm going to get 0.33 repeating meters per second squared to the right. I'll do F equals ma for this guy, but I'm putting in a negative 20 because if to the right is positive, to the left should be negative. And I get a negative 0.25 meters per second squared. So the forces are the same, but the accelerations are not because the masses are not. The big guy doesn't accelerate as much. So what happens to the center of mass? What happens to the whole system? Does it accelerate anywhere? The answer is no. These are internal forces, and on the entire system, they cancel out. So the system can't accelerate anywhere, but individual components can. Doesn't this look familiar? Let's say there's no friction. Could you find the acceleration and the tension? Now pause that video. This is the weight of the falling mass, which will accelerate the entire system. The tensions in the rope are internal if I consider this to be the system. All the pulley does is it changes the direction of these forces. And you can imagine the system looking like this. It's just like what we started with. A couple of masses, no friction, with a force pulling on them. So we write F equals ma, and the only force accelerating the system is going to be 0.588 newtons. And the mass of the system is both of these times the acceleration. I get 1.28 meters per second squared. And now how am I going to find the tension? Isolate that object. The only force pulling it forward is the tension, the mass, acceleration. And yeah, we get 0.511 newtons. Now, could we isolate this object? We have the force forward minus the force backwards equals the mass times the acceleration. And it should be 0.511, the same as this tension. The tensions are the same as long as the pulley is frictionless and massless. Here comes trouble. We lost the wheels. Now we're just dragging on the surface. So this is with friction. Now without any wheels, that's just not going to accelerate this block. But this will. So let's say we had a coefficient of kinetic friction of 0.25 on this block. The system is moving forward. Now we can find the acceleration and the tension. Force of friction must be going in the opposite direction of the velocity. And that's equal to mu k Fn. The block weighs 3.92 newtons, and the table holds up 3.92. So we have a 3.92 Newton normal force times the coefficient of kinetic friction, and my friction is 0.98 newtons. So now I can see I have a forward force and a backward force acting on the entire system. These two forces cancel out, and we don't use them. Forces forward minus forces backward equals the mass times the acceleration. And that, again, is the mass of the whole system, giving us an acceleration of 2.8 meters per second squared. Now, what about the tension? Isolate either object to get the tension. I'll look at the block. The weight and the normal force cancel out. So when I start with F equals ma, I have these two forces acting on the block. Tension forward minus the friction backwards. Then I have the mass of the block times its acceleration. And I have a tension of 2.1. Does that make any sense? The block is accelerating in that direction. The tension should be bigger than the friction, and it is. Well, that should be the same tension over here. Should this be bigger or smaller than the weight? It better be smaller because this block is accelerating in this direction. We can check our work using F equals ma. And now we'll solve for the acceleration. Hey, we get the right acceleration. It worked out. All right, last one for this video. We have a 1.8 kilogram hanging mass on a frictionless massless pulley. We have a frictionless cart of 3.6 kilograms and a 20-degree angle. Can you figure out the acceleration of this system? We have a force of 17.64 newtons from the weight of that object. The weight of the cart is 35.28 newtons. But that force is not going to make this cart go down the hill. It's the parallel component of that force. The perpendicular force holds the block to the ramp, but the ramp is going to push back with the normal force, and they'll cancel out. So I take the weight times sine of 20, and I get a parallel component of 12.066 newtons holding this thing backwards. So I start with F equals ma. I'll say this is the forward direction because that force is bigger than this force. So I have the forward force minus the backward force, and I get 5.4 kilograms for the mass of the whole system times A. And I got an acceleration of about 1 meter per second squared. Now, what if I set this thing up wrong and I ended up with a negative acceleration? That just means the acceleration is going this way. Of course, that could happen if this force was bigger than that force. And now for the tension. It really won't matter which block we isolate. We have the forces forward minus the forces backward right here, the mass of that object as my system, and the acceleration. And we get a tension of 15.78 newtons, which is smaller than this force, and that makes sense because it is accelerating in this direction. And that would agree with the tension that we could find using this system, because 15.78 is bigger than that force, making the cart go uphill. Tons more practice on the worksheets. You could probably do all of these now. Check your answers with the answer key, all worked out.